Hello everyone, my name is Viraj and today we'll be having our post-contest discussion for Leetcode Biweekly Contest 144. We'll be solving all the 4 problems. Let us begin. So I'll be moving on to my first problem, stone removal game. So this was a very simple and easy problem. Alice and Bob are playing a game where they take turns removing stones from a pile, with Alice going first. Now Alice starts by removing exactly 10 stones on her first turn. Now every subsequent turn, each player removes exactly one fewer stone than the previous opponent. The player who cannot make a move loses the game. Given a positive integer n, return true if Alice wins the game and false otherwise. Okay, so let us try to generalize this problem and understand what are they saying. It's a very simple problem. Basically, 2 players are playing, very famous players, Alice and Bob, and you have some stones to start off with, which is exactly 10. So you start off with 10. And that is like the number of stones you want to remove, but you actually have n stones initially with you. Okay, so what we do is we say Alice is going to play first, and it's a simple stone removal sort of a strategy. From n stones, Alice will say I'll remove 10 stones. So now the new value of n goes to n minus 10. Then next time, the number of stones that I want to remove will decrease by 1 and this will become 9, and Bob will say, okay, I want to remove n, like whatever is this value. Let's say this value became n dash. So now n dash went to n dash minus 9, and so on. This process has to be followed, as in the original n has to be decreased with 10, then 9, then you have 8, then you have 7, so. This is what we are trying to do in the problem. Now, of course, there's going to be a moment of time when I cannot remove the number of stones I want to remove. As in, let's say Bob in his turn wanted to remove 9 stones. But what if this n dash value was actually less than 9? You never had 9 stones to remove. So will you say Bob can remove 9 stones? This operation will never be possible. And this will denote something known as saying Bob lost the game. That is why if you go back in the problem, what are we saying is every subsequent turn, each player removes exactly one fewer stone. So first 10 stones, Alice removes, then Bob removes 9 stones, then 8 stones, 7 stones, 6 stones. That goes to happen. But whenever a player cannot make a move, as in he or she cannot remove the number of stones they wanted to do, we will say that that player lost the game. So you have to return true if you think Alice wins the game, else false if Bob wins the game. Okay, so this is a very simple problem. If we see at 12 over here as an example, we'll get a very good strong intuition in our head of how do we simulate this problem. N is 12, so you start off with removing 10 stones, where Alice is starting first. Alice removes, 12 becomes 12 minus 10, that is 2. Now it is up to Bob, so Bob removes basically 9 stones. But can Bob remove 9 stones? No, there are only 2 stones left. So from here we say come out. You cannot do anything, and oh no, because Bob was not able to perform any operation, Bob lost, or indirectly Alice won. Okay, that's why I think we will remove, we have to return true because we think Alice has won the game. Similarly, you can simulate on this. N is 1, so of course Alice cannot start off to begin 10 stones in the first turn. That's why she loses. So indirectly Bob wins, so you return false. Okay, so a very simple and simulative based problem. Now, because this is an easy problem in Leetcode, we can come up with some mathematical sort of a strategy in this to maybe shift our time complexity to a very good boundary. But the argument over here is that n is very small. So n is given in constraints of 50, which actually hints us that this problem is a brute force problem. How about I actually simulate what I want to do and I'll be good to go? Because if I'm talking about 50 at very large max sort of a number, then let's say n begins with 50. So you will be removing from 50 10, so this becomes 40, then you will remove 9, so this becomes 31, then 8, then so on, 7, 6, and then after like a brief moment of time, n will become 0. And this whole chain of operations is not going to be very large. So this is simulated. This is something that we can brute force out. This means I know that I can run a solution that is sort of very basic variable maintaining sort of a solution. I can say that, okay, let me have a variable called as turn. Let's say turn is 1 or 0 accordingly. Like this is just implementation. 1 I can say is for Alice. If it's 1, I know it's Alice's turn. Else it's Bob's turn. Not a problem. Then I say, okay, the stones I want to remove currently starts with 10. And then of course I have an n value. So maybe I can run a while loop on this n value till I feel that n is positive, as an n No, I'm so sorry, not positive. You can say till you feel that n is actually greater than the removal stones that you want. Like, so we can name this like stones only. So we can say, okay, till n is greater than equal to the stones that I want to remove, then I know I'm going to perform my operation. That is, I want to reduce from the value of n the number of stones, and then I of course want to reduce my stones by 1, and then I want to make changes. I know that right now I start off with a turn as 1, that is Alice's, so I want to make the change that turn goes from Alice to Bob, or vice versa in every sort of a while iteration. Okay, and when this happens, when I finally come out of this while loop, I know I'll be coming out of this while loop when this condition becomes false. That is, you don't have sufficient stones to start off with. N is not greater than or equal to stones, so whichever number of stones you want to remove, you cannot do that. And when you come out of this loop, your turn variable will actually store whose turn was it when you came out of the loop. Whose turn, you can write whose turn was it when n became less than stones, and this is going to be saved in this turns variable. Very simple pseudocode. And when I come out now, because I know this turn variable is getting me the person whose turn it was, so I know that person is losing. So if let's say that turn is actually 1, it's Alice's turn, so I know that Bob is winning, and if it's Bob's turn, then I know Alice is winning. Okay, so this is a very, very simple simulative based problem. Let us look at the code part to understand how can we do this. So just as I depicted the whole pseudo structure, that is what I'm going to follow. I'll have over here the stones variable, that is 10. So that starts off with, then the turn variable is 1, 1 is for Alice, 0 is for Bob. And then n is, while I think n is greater than or equal to stones, I'll remove some stones from n, that is this number of value. Then I'll decrement stones by 1 because I know in the next subsequent turn, the number of stones I want to remove is lesser than its previous value, so decrease 1. And then turn changes its value from 1 to 0 or 0 to 1, vice versa. So to do that, this is a small trick. Turn equals to not of turn. So not is a bitwise not operator. You run this on this 1 or 0 value. So 1 will become 0, 0 will become 1. So it basically flips the whole number 1 to 0, 0 to 1. Now this basically helps me finally come out of the loop and answer this question, whose turn was it when you come out of this loop? If that turn is 0, that means Bob was losing, so Alice was winning. So if turn was 0, that means you need to return true because that means Alice won. If turn was 1, then that means Alice was was the player who was not able to fulfill the condition. So that means in that case, Bob wins. So otherwise, this would return the false check. So very, very simple problem. Now, what about the time complexity? So in worst case, like you're starting off with n equals to 50 stones, right? In this case, and then you're removing 10, then 9, then 8, then 7, then 6, and so on, so on, so on. So if you actually quickly calculate this on your calculator or by pen and pencil, you will figure out that like I can go to a sum of 10 to 10 plus 9 plus 8 plus so on till 3. That would approximately give you a sum of I think 50 to 51 something. And that is where you know you will stop because that crosses the 50 boundary. So approximately it's basically like maximum 7 to 8 moves is when you stop. Now 7 to 8 moves is almost constant. We cannot consider 7 to 8 moves as a number of value which can be denoted in number in terms of n. It's very low number of operations, so it's almost next to constant. That's why I can just report my time complexity for this problem to be constant. Okay, now what about space? I'm not using any extra space in terms of any data structure. I simply have some variables, so I know space is also pretty much constant. And this definitely submits out in the accepted solution, and I know that this problem is fully solved. Okay, so I think the catch in this problem was to understand that, okay, there is a simulation that can happen based on the judgment that, okay, the constraints are very low. If you are able to understand this, of course, the first problem will be very, very easy for you. Okay, so let's move on to our second problem. Okay, so shift distance between two strings. You are given two strings SNT of the same length and two integer arrays next cost and previous cost. In one operation, you can pick any index I of S and perform either one of the following actions. You can shift Si to the next letter in the alphabet. If Si equals to Z, then you can replace it with A. So this is a line that we'll understand when we fully discuss the problem. Let's move. This operation costs next cost of J, where J is the index of Si in alphabet. Okay. And the other operation is you shift Si to the previous letter in the alphabet. If Si is equals to A, you should replace it with Z. Now this operation costs you previous cost of J, where J is the index of Si in the alphabet. So these like are the two operations given. Now, what are we trying to calculate? We want that the shift distance is the minimum total cost of operations required to transform S to T. We want to return this shift distance. Okay, so let us try to generalize this problem and see that what is being asked of us. Okay, so we have been given two strings S. So this is string S and this is string T. So we'll actually take some examples so that it becomes clear. Let's just talk about example 2, lead and code. Okay, so I'll use that. You have S equals to lead and T equals to code. So basically we want to convert lead to code. This is something that we want. And to do that, you have been given two operations. Okay. Now let's try to understand these operations very clearly because it might get confusing. First operation is you will shift SI to the next letter. So actually before we even understand the operations, let's actually write the alphabets down in a very simple order from left to right in the lowercase format, because that's going to be very helpful, because like it's obvious we are using that in the question. So this is like A, then you have B, then C, then D, then E, F, G, H, I, then I can write J, K, L, and so on, so on, so on. To the last letters, you have X, Y, and Z. Now, it's very obvious. There is one thing we can even add in this, is because all these letters are, if we want to represent them in simple index formats, you can represent them from 0 to 25 indexes. As in, you can say that, okay, A was an index that was mapped, like A was a letter that was mapped to index 1, then B is, A was mapped to 0, B is 1, C is 2, then D is 3, 4, so on, so on, so on. This streak can continue, and then you have like something like 23, 24, 25. So this is the overall, you can say, indexing that is also being done to the letters. Now, why is this important? Because if we now go back to the problem, when we read the operation 1, what is it saying? You have the power to shift S of I to the next letter in the alphabet. So first of all, we wrote down the alphabets, so that's clear. What do we mean by next? Let's just say that there is some letter B. For example, there's a letter B. So if I say I want to shift it to the next letter in the alphabet, basically it means that in this ordering of alphabets that I've written, B can be converted to its next letter, that is C. So you can see B to the next is C. Now to do that, like when I know I have the power to do that, it comes with a cost. So this cost is basically this next cost J, where J is the index of SI in the alphabet. But actually, before we even discuss the sentence, let's see what's this. If S of I is Z, you should replace it with A. So basically, if I took an example of B being converted to C, you know that B as a letter has a next letter, that is C. Maybe I could have asked you that you want to convert X, then X has a next letter Y. Maybe I asked you the same question for Y, had the next letter as Z. But if I ask you this question for Z, if let's say you are at Z and you want to convert it to its next letter in the alphabet, can you understand that there is no next letter to the right of Z? Of course, I can see very clearly there is no next letter to the right of Z, which means that there is some catch over here, and to resolve that catch is why they have given this line over here in this operation, that if you are at Z, you can replace it with A. That means that it kind of has a circular nature. Being at Z, you don't need to see, okay, there was no next letter coming over here. That next letter can act in circular format back to A over here. This is actually a very, very important point to understand. So it kind of creates a circular chaining from if you are at Z and you want the next letter, come back to the initial position and start off with A again. Okay, so this is the meaning of that sentence. I hope this should be clear. Now comes the main part. When I convert some letter to its next letter, it comes with a cost. What is that cost? How do we find it? So for that, they have been given two integer arrays. One is next cost and previous cost. So we'll actually come to the example which took lead and code. Next cost array and previous cost array is something we can write down. So I'll write this down over here. You have a next cost array, which was actually like of 26 size, and it was very easy for us that all the numbers are ones. We can just write something like this, 1, 1, 1, 1, 1, so on. Then you have 26 ones. Of course, they are also mapped to some indices, right? In an array, you have indices 0, 1, 2, 3, 4, and so on. These indices go to the last position, that is 25. So now it kind of makes sense also that the next cost size is 26, basically till 25 indexes. And it kind of is giving us a hint that it's basically for the letters that we were talking about, since we have 26 letters. And in the same manner, you also have a previous cost array. which is somewhat of the same nature. You have 26 length over here also. And in this example that we took, we have 26 ones to the last position. And of course, these are again also mapped with the same indices. This is like 0, 1, 2, 3, 4, and so on till 25 position. Okay, so I hope this should be clear. Now, when I say that I converted B to C, B of course has an index that is mapped. We know that B is at the index 1 and C is at the index 2. So they are saying that if you make a change and move the SI to its next letter, you will incur a cost of next cost of J, where this J can be replaced with the index of SI in alphabet. So index of SI means, what is the index of B in the alphabets? We wrote it down, that is 1, which means that if I talk about this value, that is next cost of 1, this value, this is something that I want to use with me. Okay, so this is the whole argument. That means I will add cost of 1 to my answer. Now this could have been some other value also, maybe some value V. Effectively, that is the value I would have added, because this signifies that I'm changing my letter from index 1 to index 2, or basically B to C. This is very, very important. Okay, now this is operation 1. Now what is the second kind of operation? It's the same but in a different reverse manner. When we talked about next letter, in this operation we talk about the previous letter. So I can just take the same example. Maybe I have something like this. Maybe you wanted to convert the letter D to the letter C. In this case, you are trying to go from index 3 to 2, right? So you would have done the same thing. You would have said, okay, D is going to its previous letter C. So fine. Where do I take the cost from now? I don't take this from next cost. I'm going to take this from previous cost. So same sentence, this operation is going to cost previous cost J. So I'll say, okay, convert, like the cost would come to convert 3 to 2, that is basically this value cost. So this value again is 1. That's very useful to us. But then again, this would have been some other value V also. We would have actually added that V value. Okay. But here you add 1. Now, same as we discussed this sentence in the next cost, that is if you were at Z, you would have converted to A, is the same logic that applies here also. If let's say you are at B, then you know there is a previous character that's A. But what if you are at A? You can see there is nothing left to A, which means that this connects a circular manner again back to Z. So if you are at A and I ask you what's the previous letter, you will report that to be Z, come in a circular manner and again start off with Z. Okay, so this is the whole idea. This is how we are calculating this operations that we're talking about. Okay, operation costs that we're talking about. Great, I hope this should be clear. Now, what's the problem? So the problem is that you want to make S equal to T. So of course we want to convert lead to code, and to do that you will have this cost calculation that will come from conversion of letters and so. Whatever is the total cost you calculate, it is called the shift distance, and I want that to be as low as possible, and I have to report that value too. So in this example case that we took, the answer arguably is 31. Why is that? Let's quickly understand. So they are saying, okay, let's say I was at index I equals to 0. That is basically this index where the letter L is kept. L would wish to convert to C, of course, because L right now is in the S string. S wants to come to T. That means this letter has to match. So this letter should become C. So basically I'll say that how do I convert L to C? Let's find that. So they are arguably saying that you can do shifting of S of 0 9 times to the previous character. That means if I come back over here in the problem, basically I would require something like this, that there was L given, okay, and L wants to convert to C. So I will have to find the indice of what L has and the indice of what C has. And because I'm making L go back to C, so I'm sort of taking the backward direction, that means I would use the previous cost. So somewhere wherever L index is kept, wherever L's index is there, and wherever is C index would be, I think, at index 2, of course. So index 0, 1, 2, 2 index is where C is there. So whatever is the cost I would incur from jumping L to C is basically I would accumulate, and that would be reported as the cost from L to C. Now over here, we can understand that when we want to go from L to C, basically L to C has this jumping that's going on. You convert from L to the previous letter, to the previous letter, to the previous letter, and so on. And this happens till you reach C. How is that possible? Like you can imagine over here also, you have L to K, J, I, H, G, F, D, C, and D and C. So this kind of have 9 jumps, right? You can understand this as 9 jumps. And actually in the previous cost array, we were easily able to see that every value was 1. So it basically means that if you are jumping from L to C, you would have a total of 9 jumps of 1 cost each, effectively giving you a total cost of 9. That is why this cost is 9. Okay, I hope this should be clear. And this is what comes from L to C. Similarly, they're arguing that if you want to convert the next letter E to its letter that should go to O is 10 times, you can do that to the next character jump, and that would give you a cost of 10. So now we would concern ourselves with the next cost array. Similarly, this one is previous times only with a cost of 1, and then the next character cost with 11. Effectively, total gives you 31 as a cost, and arguably this is the lowest. Okay, so I hope the problem should be clear. The examples are clear. You can just pause the video, maybe create one more example of your own, and maybe even understand example 1 in some time, so that you're able to get the whole grip of what is happening in this problem. It might be confusing at a larger picture. Okay, great. So now comes our main intuitions this problem. How do we begin solving? So it's a very good point to note that if we understand example 1 and example 2 clearly, we'll able to get one intuition straight off the bat. That is, of course, I want to calculate the answers independently. When I say that L converts to C, E converts to O, D converts to D, T converts to E, whatever is their individual costs in the minimum order, they're kind of independent with each other, right? Whatever happens when I do from L to C doesn't bother myself with what happens when I convert other letters to other letters. That means I basically can calculate the individual cost of all the conversions, that is in this case 4 conversions, and add everything up. That is going to for sure give me the answer. So this is like observation 1, that individual cost is cumulated. Okay, it's cumulated finally. So this is a very important point. Great. Now after this, over here, we just took this blindly that when you wanted to convert L to C, your total cost would have been 9. What is the path that you took? You took a path that was previous, right? So you said, okay, starting at L, I'll jump like this, go to the left, jump like this, and I'll come to C. So this was fine. And you said the cost was 9. But the problem over here is, we although realized and see that there is only one path, there is a possibility that there is one path more. To be specific, there are always 2 paths you can take. Why? I'll draw this with green. I could have argued that standing at L, rather than coming back to C in a backward direction, maybe I could have taken a path like this. Maybe I could have actually gone from L forward, so on, till Z, then came from Z to A, and then finally landed from A to B to finally C. Maybe this could also have been followed. This green path could also have been followed. This would have, of course, given me a different cost, and this cost would have been calculated from the next cost array. So remember, this is going to come from the previous cost, and this is coming from the next cost. So maybe that cost would have been different. In this case, when we calculate this cost actually for this particular test case, you will understand that taking this path on the previous cost array, that is sort of a backward path or in the left direction, was more favorable. That is why we said that, okay, add up our answer 9 for conversion of L to C. But maybe it could have happened that in some other case, this path, that is the forward green path that we took, would have been much more preferable. It can happen, right? This is this test case, so we are limiting ourselves to the value, but that's not sure. Maybe the next cost and previous cost array were given in such a manner that this green path was more favorable. So to generalize this problem, this gives our next hint that although in the problem example it was clearly given the cost is 9, but actually we have 2 paths. That's the main idea. So we need to understand that we can calculate the 2 paths answer separately, and then whatever is the minimum out of them would definitely tell me that what was the best case to go from a letter in S to a letter in T. This is actually a rudimentary idea. Let's actually discuss this further. So I can draw some 3 cases in this thing. I can say, okay, what happens when you have S of I, if we are talking about the, because we know that the size of S and T are same, so we can simply say S of I equal to T of I, right? The same index position. What happens when S of I is actually less than T of I? Okay, as in You had some letter in S which you wanted to convert to T, but that same letter in T which you want to go to is actually greater. And what happens when it's greater? So these are arguably the three cases I can create, right? And in these three cases, we can get the answer separately. For the first case, of course, the answer turns out to be 0. Because I know that if both the letters are same, do I need some conversion independently? If let's say I wanted to convert from L to L, will I need that? No. Because I wanted to convert from a different letter to a different letter is because all this calculation came into picture. So the first case gives me an answer 0. It's something I don't even need to bother myself with. Okay, now what happens when S of I is less than Ti? What happens when S of I is greater than Ti? So we'll take these separate cases. So let's take the same example that we were talking about in the test case. You had to go from L to C, but let's take a reversing. You had to, let's say, go from C to L. So C is a letter that comes before L in the alphabetical order. So this makes sense. This can be possible one of the cases example that there is some letter which is lesser and you want to go to a larger letter. So an example, let's say you want to go from C to L. So what we saw over here, we'll try to rub it out and discuss this again. What is actually happening? Okay. So you're standing at the letter C and you want to go to the letter L. As we discussed, there are basically two paths to follow. We don't know the next cost and previous cost array as of now. We're not taking the same case. We're simply saying that there is some paths you want to follow. How do we get those paths? First of all, let's imagine what are those paths. Very simple. You can go and take the forward path. So you can say, okay, maybe I start with C and go in the right manner. So I take C, next letter cost D, then D, next letter cost E, then F, then G, then H, so on, so on, so on. I do this and I land till L. So either I can take this sort of a forward cost path. This is one of the green paths that we're talking about. Or I can take the previous cost array into picture and create a backward path. As in from C, I don't take and go right to L. I do the opposite. I go to B, then to A, then from A, I actually come back to Z, and so on, so on, so on. I move back to L. This is something I can do otherwise. So the white path is sort of this backward path, and then this green path is the forward path. Whatever is the minimum out of these two paths, when I calculate the costs from the next cost and previous cost array, should be the answer. This makes sense. So I can write this down, that I can have a forward path in this case, where you directly go from C to L. Okay. And otherwise you have some sort of a backward path where you go from C to A to Z to L. Great. Now what's the answer? Answer in this case is minimum of this forward path and this backward path. Great. I hope this should be clear. So this is basically case number 2. Now actually quickly discuss case number 3 so that it makes much more sense, and then we'll come to the main part of this problem. Case 3 can be just the opposite as we discussed. What happens when you do the just opposite thing? S of I is actually greater than T of I. So maybe I can take the reverse example. Let's say you wanted to go from the letter L to the letter C. So you can do the same thing. You can say, okay, there is some sort of a backward cost. Okay, some sort of a backward cost where you could have taken something like going from L to C directly, right? L to C directly, or you had some sort of a forward cost. In the forward cost, imagine, you can visualize this very clearly. From L, you went back to C, or from L, you would have gone forward to Z. Then from Z, you would have jumped to A, and then from A, you would have gone to C. So it kind of follows the same strategy or analogy over here. And when I said what's the answer or what could have been the answer in this case, this answer would have been the minimum of forward and backward. Great. I hope this should be clear. Okay. So now when we have understood that, let's try to understand what is the main idea in this problem. We got this that we want to calculate the forward and backward path, but how do we get that? How do we get that very efficiently? Basically, if we observe, make some observations over here. When I talk about the forward path, I was talking about case number 2. In the forward path, I am concerned with the next cost array. Okay, great. That makes sense. But in the next cost array, I am basically concerned with all the values that fall from conversion of C to D, then so on, so on, so on, to finally K to L. That is basically this much segment of portion that would have followed up in the next cost array is what I am concerned with, right? If I am able to get the sum of this range in the next cost array from this index to this index, as in whatever index as is there for C to the index where K is placed, I know I will get the answer, because that cumulatively would give me the cost of conversion of C to L. This is observation. And the second thing is, if I wanted to calculate for the backward path that is coming from the previous cost array, it is kind of broken into two segments. You first will have to calculate the segment sum which comes from B to A, this range, and then the other would have been conversion from Z to Y to X to so on till this before L position, that is whatever letter was here, let's say whatever CH letter was here, then from that letter when you wanted to convert to L. So this two white boxes sum actually tells you what's the backward path cost. So effectively, when I say you want the forward cost and the backward cost, you are looking to calculate the continuous sum on the array's next cost or previous cost, whatever case falls, and you want to or definitely wish to calculate this very, very quickly. Since if you do this by brute, you will definitely reach a TLE solution. This is where the whole concept of the problem lies. Up till here, everything was observations. After now, we'll discuss implementation. We'll see, okay, this is something that we know, this is something that we want to do, but how do we do that in code terms? How do we get this quickly? Okay, so this is where a concept that will come into picture is called prefix and suffix sums. Okay, so this is a very, very important concept. This is like frequently visible in problems of Leetcode for the problem 2 and problem 3 most of the time. So this is a concept we actually discuss in TLE level 2 also. So definitely check that part out. So what is this concept actually? Let's get a quick overview. Let's say there's an array like A, B, C, D values. Then prefix sums is a new array that's created, or prefix sum is a new array that's created on the original array A, where every ith index has a value, and that ith index value represents the sum of all the elements from left to that index or 0 to that index I. Basically, that would mean this value would have been A, this portion would have been A plus B, this would have been A plus B plus C, this would have been A plus B plus C plus D. So like sum till here, then here, then here, then here. And when I say what is suffix sums, suffix has the meaning from the back. So it kind of creates the same idea, but from the back side. So now you would have something like D from the back, then D plus C, then D plus C plus B, and D plus C plus B plus A. Now the idea is, why is this very helpful? Why do we calculate prefix and suffix sums? Because the main problem over here was to calculate continuous sum segment, and that is very, very easy to do with prefix and suffix sums. How? Let's just say, for example, that you wanted to calculate the segment sum from here to here, that is basically B plus C. To do that, what we can do is either we do a brute solution and we run from positions this to this, maybe this position L to R, or we calculate the sum, use the value of sum till position R, and from that we subtract whatever sum was contained till position L minus 1. So if we note down the positions like A plus B plus C minus this position, that is minus A, this effectively gives you B plus C, which was the desired output. You wanted the sum in the range from L to R, where L to R captured B to C. Okay, for example, like again, this A, B, C, D's are like numbers that I've taken. Don't confuse that with the whole idea. All right, so this is where prefix sums comes into picture, and this is how prefix sums is useful. So using this idea, if I would have argued that if you know this idea now, will this problem become much more easier? Of course, because now if I want to calculate this next cost and this previous cost, or basically the segment sum on this previous cost and next cost array, it's going to become very, very easy. Okay, let's understand how once again. So what I'll do is I'll create a prefix sum sort of an array on the next cost and a suffix sum array on the previous cost. Why am I going to do that? Because how can I, like if I look over here at the whole idea and how is that useful to calculate, let's actually rub this out. Let's say I was talking about the forward path that is going from C to L in the right direction. Now you wanted the segment from C to basically K. How do you get that? If you have a next cost prefix sum calculated on that prefix sum array, basically I can get whatever is the cumulative sum till k, okay? And from that I can subtract whatever was the sum till c. So not c actually, till b. So will that not give me the segment sum from c to k? Yes, that will actually give me the segment sum from C to K. And this is calculated on the next cost prefix sum array. So prefix sum was useful over here. That is why we calculated a prefix sum array on the next cost. And similarly, when this forward path has been calculated, if I picture that, how would a suffix sum array help you on the previous cost? In this previous cost, you would have wanted to calculate first of all this segment and then this segment, right? So how do we do that? Over here, when we want to calculate the segment, from like this part, this small part, we can do something like this. Get the suffix sum till a. From that, remove the suffix sum that came till c. So this gives you this segment. Great. And the other segment, how do we get that? Same thing. Get the suffix sum till l, the position of l plus 1. And from that, basically remove the suffix sum till this last location. Basically, last location is nothing. So after z, there is nothing. Basically, you remove 0. So effectively, till this whole suffix length is what turns up at as answer. So this was only possible if you had a suffix sum array on the previous cost. And this quickly helps you calculate the backward cost. Okay, so now if you actually pause the video and run this example, let's say maybe through the third possibility of cases where you wanted to go from L to C, same ideology, you will be very you will understand this, how helpful is prefix sum array going to be when we want to calculate the forward cost, and how easy it would be with the previous cost suffix sum array when you want to calculate the backward cost. So this whole idea of prefix and suffix sums is basically helping me with the continuous sum calculation in some range to some range, and that is going to help me quickly get the forward and backward costs in both the cases, whichever case it comes up to be. So now the problem simply remains is I code it up, I bother myself with understanding which case am I landing at. Am I at case 1, 2 or 3? If I'm at 1, I simply add a cost of 0, nothing happens. If I'm at a cost of 2, and if I'm at a case 2, I'll realize that, okay, let's calculate the forward and backward past, get the minimum. And if I'm case 3, great, let's still get the forward and backward cost, but in a different analogy round, we'll handle that case, of course, when we write the code, and same idea, get the minimum again. And then do this for all the I running from like 0 to n-1, basically calculating the answers for every conversion of every SI to every TI and accumulate everything up. That is going to be the net minimum, because everywhere you have taken the minimum when we wanted to convert each letter to each letter in that initial, like wherever that index I had. So cumulatively for all indexes, that answer is going to give me the best possible case. Hence, this shift distance value is calculated, and that's the best answer. Okay, so now if we come back to the case example 2, it's going to be much easier. You had this total cost 9. You can see that it would have come somewhere around previous cost, in the previous cost array, somewhere around here, wherever L was, to when you went to C. So somewhere like this, like 9 cost, something like this, like I think this much 4, then this is like 5. So I think from here to here, yeah, this would have been something like a 9 cost, which you incurred. And in the other way around, if you wanted to go in the forward path, that would have been some cost again, but that would have been greater than 9, because that would have come from the next cost array, somewhere around like starting from L going to all the way up to Z, and then from previous going from A to somewhere going to C. So that is going to be a larger cost as compared to 9. That is why in this case we took 9. There was no coincidence, right? Same thing happened with when we wanted to convert from E to O, E to D, and T to E. Cumulate everything up, gave you an answer of 31. Since we took minimum every time, hence 31 was also the minimum overall. Okay, so this is the whole idea and the problem. I hope you like the problem. Let's actually discuss the code part now to get a grasp of how do we do this. Okay, so great. So now, as we discussed how our normal prefix and suffix sum should look like is what we're trying to do. We'll first calculate the size of the string. It is very helpful, n size. Then I'll create a next cost prefix sum array of 26 size, everything starts with 0. A previous cost suffix sum array, that is 26 size, again starts with 0. So my first values are declared. So I know that, like, if I go back in the problem here also, we saw that the prefix sum starts with like the first value, same copied, that is A. So I'm basically declaring that for myself. So I'm saying, okay, next cost prefix of 0 is basically the first value in the next cost. Similarly, the last value in prefix cost suffix is the last value for the prefix cost. Now a simple loop runs from 1 to 26 because 0 index has already been covered, and next cost of prefix of I becomes whatever was the prefix cost plus this current cost that is coming into picture. Basically, whatever is the cost till here, you add with this current number, so the B, so that's A plus B. Next time, whatever is this cost till this location A plus B, you add that to C, so A plus B plus C, so on, so on, so on. So this keeps on happening and you get a next cost prefix sum array. Same is an ideology that happens when you do a previous cost suffix sum array. So you start with 24 because 25 was the last index, so you have covered it. You want 24 greater than or equal to 0, I minus minus. Current value should be the right value of prefix cost suffix sum plus whatever is the current previous cost at the ith value. Add that up and that gives you the suffix sum array created. Okay, now comes our main logic. We have a cost variable, starts with 0. We run a loop and then we simply ask the case, what are we standing at? So if let's say we are at a case of SI not equal to TI is when we of course want to do something. If SI is equal to TI, we don't want to do anything. So it's fine. We have a simple if check. Then we actually get the indices first, right? With this mapping that I was talking about is something we need to get first. How do we get that? This is a very cool trick of how do we get the indices is we can actually subtract the SI character. From it, I can take out the ASCII value of the small letter a. Why would that be helpful? Because basically this SI would have been a letter again in the lowercase characters only. From that ASCII value of that small letter, if I subtract the ASCII value of A, which is the first alphabet in the whole range, then I will actually get the mapping of that letter in terms of 0 to 25 range. All right, let's actually give you a small example of that. Let's say like C had some value of ASCII, like to be specific, it has 99 to be specific ASCII value. All right, and A has a ASCII value of 97. So basically, if you make 99 minus 97, it basically turns out to be 2. Now 2 is actually very useful because if you remember, C as a letter is actually from indexes 0 to 25, it should be mapped to the index 2. So this basically helps us get the indexes quickly. Start becomes the index of that start letter where I want to start off with S of I, and then this end letter is T of I minus A, same thing. So I basically want to go from start letter to end letter. I have a forward cost, I have a backward cost. If I am at case 1, that is S of I is less than Ti, or basically start index is less than end index. How do I get that? First, I get the forward cost. What is the forward cost? Forward cost is basically, so if you go back in an example, we had this. Let's say forward cost means C to L. So that means you directly jump. So if you go back in this array over here, you basically make something like this. Till K minus whatever is there till C minus 1. So before C, that's B. So something like this is what we want. So we'll actually do that. We'll say, okay, next cost prefix of end minus 1 minus. Now there is a small check that we have done over here for overflow. Of course, we want that we make start minus 1 as an index use in this picture, but start minus 1 index should exist. That's why we are checking, was start greater than 0? If start was greater than 0, then start minus 1 index would exist. Hence, I will get the prefix next cost of prefix of start minus 1, else I'll get 0. This handles the case of overflows. All right, because what can happen is maybe the segment that we're talking about was only till this location, and then the other segment that we're talking about was this location, right? So this location doesn't make sense. That is basically I want to subtract only 0. So that is what we are handling over here. Okay, so this is the case in the next cost array when you get the forward path, and same is the argument we do for backward cost. We first go from that current letter all the way back to A. Then like from A, we make our, like there's a plus sign. Then from A, we make ourselves go to Z. That is already done. That was already calculated. From Z, we make ourselves go back to whatever was that end letter plus 1. So if you go back, basically this is calculated right now. This is the segment. And then simply in the region, this is calculated. So how is the first thing calculated? It's basically calculated like this, that you have till A, and from that you subtract till C. This is there. And then you have overall till L plus 1. That is why N plus 1 is written. Okay, so I hope this code part should be clear. And checks are again put for the overflow part. Start plus 1 should be less than 26, so it should exist. Similarly, if N is 25, then you would only want to take 0. If N is not 25 is when you want to take N plus 1. Great. So this is basically case 1. Now we discussed only, like not exactly case 1, you can maybe call this case 2 and case 3, how we discussed in the problem. All right. And when case 2 is clear as day is the same idea when we would be using for case number 3. Over here, backward path is calculated in different manner. You go from L to C. So backward path is on the previous cost suffix array. Do this the same manner, check for overflows, and you also get the forward cost in the same order of how you calculate backward cost in the case 2. So the structure changes, the variable names changes and everything, but if you visualize this clearly, the same ideology is followed in this part also. And then when you have covered both the if and else cases, you actually get the best forward cost and backward cost for conversion of start letter to an end letter. You add that minimum out of those two in the main cost. If you come out of this for loop now, you would have the best minimum cost for all the conversion of letters, since independent values, independent costs were what we wanted, return the main overall cost. This gives you the right answer. Okay, so this is a very clever and a very fun problem on the concept of prefix and suffix sums. Without that problem, without that concept, this problem would have been very tough to solve. Okay, so now what's the time complexity? I actually wrote some parameters quickly over here also. You have this order running over here in 26 size. This also runs in 26 size, sort of something in 26 order. And this runs in n order. So overall, you have something like inside this, since you have constant calculation only, this is pretty much pre-calculated. So we get a time complexity that runs in O of n order, since O of n was the superseding term in all the time complexities. Now n was in 10 power 5 picture. That is why we know that we have a 10 by 5 order. This definitely works. It's well within our boundaries. So this is good to go. What about space? So there is some space I'm using for the previous cost and next cost array. It's 26 size, but there is actually some space which comes from the string capacity. String capacity size is dependent on the size of that string, which is n. Now n being could have been the larger term. So I have just taken a generalized term of 10 power 5 order maximum in terms of space, because 26 is basically constant. We don't need to bother that with compared to n. Okay, so this gives us our time and space. Great. So this is all about problem 2. Let us move on to problem 3. Okay, so question 3, zero array transformation 3. You are given an array, integer array nums of length n, and 2D queries where queries of I is li to ri. Okay, now each queries of I represents the following action of nums. Either you decrement the value at each index in the range li to ri in the nums by at most 1, and then understand this, that the amount by which value is decremented can be chosen independently for each index. Now a zero array is an array where all the elements are 0. Return the maximum number of elements that can be removed from queries such that nums still can be converted to a zero array using the remaining queries. If it's not possible to convert nums to a zero array, return -1. Okay, so let's try to generalize this problem and understand what are they saying. Basically, you will start off with like an n-sized array, of course. So like you have been given a nums array, right? So I have a nums array. Array A, I'll call this, or not A, I can call this nums array. You have some numbers like A0, A1 number, so on till the last number an-1. So an n-sized array. Then you have some queries, okay? Queries are of the format li, ri. So basically they cover a range. This is the physical meaning. Li to ri basically means from left to right, some range, somewhere from an L index to an R index. So basically, maybe if let's say I say something like 3 to 5, then that means I'm talking about index 3 to index 5. Similarly, there will be like more queries that are given, and this is the queries array that is given to you. It would preferably, I think, be a 2D vector, since you have 2 values for every particular location. Great. All right. Now, what is the operations that can be performed? The operations that can be performed is, like if you're talking about some ith query, basically you can use that ith query to do this. Let's say this is like 3, 5. So I can select the indices, like this is A3, A4, A5, let's say, and this is like A2, and then this was A1. So basically what you can do is you can say, okay, from 3 to 5, I have the range covered. In this range, I can choose to make the number, any number I want, I can pick it up, and like independently I can work on different numbers also. So maybe I first pick up, let's say A3, and I can choose A3 to be decremented by at most 1 value. So I can choose. Now I choose A3, and then at most 1 means either I don't decrement it, or I decrement it maximum by 1. I cannot decrement it more than 1. So maybe I choose that, okay, A3 should actually decrement, and you make it A3 minus 1. Then let's say you talk about A4, you say, okay, A4 is something I don't want to decrement. Maybe like A5, okay, yeah, I want to decrement A5. So that overall would have resulted after I would have processed the query, let's just say, assuming A1, A0, A1, A2. Then this would have been A3 minus 1, this would have been A4, and this would have been A5 minus 1, and so on, so on, so on. So this is what you would have said when you would have said, I have processed the first query to my will. Okay, and this is what is given. Now, this is the second sentence, which tells us that, okay, the amount by which the value is decremented can be chosen independently. So as we saw over here that I chose A3 decrements by 1, then I chose A4 did not decrement. I did not make any dependent answer on A4 and I said, okay, because A3 was decremented, maybe I also want to decrement A4 also. It was a solely independent decision I took for A4. Similarly, it was a solely independent decision I took for A5. So they have just tried to make this in a sentence format that you have independently choosing a sort of a structure for every index. You either choose it to decrement it by 0, you either choose it to decrement by 1. That's totally up to you. So now an array 0 array, sorry, is an array with all the elements 0. So basically something like all zeros, right? If you have like n size, so basically n sized 0 array. What is the target? The target is you want to convert this array, that's the current array nums, to a 0 array. Basically all elements should become 0. To do that, you can process these queries. That's obvious. But now the action is, from these queries, I can actually remove some redundant queries. Okay, some queries can be removed, and from those queries that are left over, I can still convert my nums to 0 array. So they're asking, what is the largest number of redundant queries you feel that can be removed from queries vector, after which, even if you have the leftover queries and you process them to your will, you will still be able to convert the nums array to a 0 array. And if you think it's never possible, then you return a -1. Okay, so this is the whole problem. Let's actually see the sample case now. You have 202 and then you have the queries. So they've given a very good explanation over here. Let's say you remove the last query, that is 1 to 1. Even after that, you will be good to go. Why? Because if you, let's say, process the first query, basically first query says 0 to 2 index. So basically you can take up the whole range, because this is like 0th index, this is like the first index, this is like the second index. So 0 to 2 basically covers the whole array. Then maybe you can convert all the numbers to -1 except this middle number. So you make 2 to go to 1, 0 remains 0, and 2 again go to 1. So basically your array now looks like 101 after the first query. Then you can run the same query, that is the second query, or the 1th index query, that's again from 0 to 2, and make everything look like 0, 0, 0. So the nums converted to 0, 0, 0, and you were not using the last query at all. 1, 1 did not come into picture. So 1, 1 was a redundant query. How many queries did I calculate now which were redundant? Of course, only one. That was the last query. So I reported that as my answer. One query is redundant. One query can be removed, and I'll still convert the array to a 0 array. Now, if I would have removed two queries, you will see that you cannot do that. So 1 arguably is the answer. More than 1 is not possible. 1 is the best possible case. Okay, so I hope the sample case should be clear. This is not a very tough problem to understand. We can also look into example case 2 and example case 3, and you will get the whole idea of why is this working. Like for the last case also, it makes sense. Like if you have the query 0 to 3 and the numbers are 1, 2, 3, 4, even if you run the query on the numbers from 0 to 3 index and you subtract a 1 from each number, this number nums array will never go to 0 array. Hence the answer is -1, because nums can never be converted to a 0 array. Okay, even after you process all the queries. So this is the whole idea. I hope this is clear. Now let's look at n over here. N is actually in 10 power 5 order, which means like, and because queries are also in 10 power 5 order, which means I'm not looking for a solution that runs in sort of an n square or a q square sort of an order if q is the size of queries. I want something like n log n, or maybe O of n, or maybe q log n, something like that to come into picture, because if I don't create a solution like that, then I will not be within the boundaries of my expected time complexity. Okay, so this is a good place to start off with. This is a good intuition that I'm looking for a solution that runs in n log n or O of n preferred order. Great. Now let's actually come to discussing the main idea in this problem. So this main idea actually in this problem is sort of a greedy based idea. What is that is, so first of all, you know that you have the queries li, ri. Now, of course, these queries initially are in any manner, in any sort of an order. What we can do is, by intuition, we can sort these queries. Sort these queries. So if I simply sort the queries, they will be automatically sorted on the first value. Now, this is going to be very helpful for me. So if let's say I had some queries like let's say L1, R1, then you have L2, R2, so on, so on, so on. If you have sorted them, basically you have made sure that L1 is less than equal to L2 is less than equal to L3 is less than equal to so on, so on, so on. You have made sure this happens. And because this is like an automatic sort, so by default, L1 is first sorted, preferred on the ascending order, and then is R sorted if L are same. So basically for some case where L's are same, if let's say L1 was equal to L2, then if R1 is less than R2, then L1 R1 as a structure would come initially. So this is sort of a automatic, you can say default sort that is done in the sorting when I run a sort SQL function on the queries. Now, why is this helpful? This is helpful to do something very, very important. Let's say you start off with the first number. That is the first number kept over here. That is, let's say A0. Okay. So A0 is a number you are kept at this location. Of course, you want that A0 should go to 0. You, of course, if this is a non-zero number right now, let's say it's a number 3, 4, something like that, non-zero, you want to make it to 0. To make it to 0, you want to process the queries. You want some queries that you're able to use, correct? So now since the queries are sorted in L order, of course, standing at the first query will be more preferable because first query is of higher chance to cover this number. Since queries are sorted in L order, so this L1 value will be the lowest in all L values. So this is going to probably cover this 0th index. Maybe L1 is 0. So if L1 is 0, this means that this query is processing all the numbers or has the power to process the numbers from 0 to some index R, that is R1. So you can definitely use this query and use this query to make A0 to go to A0 minus 1. Similarly, there can be some more queries till at some particular stop location where these queries every L was 0. So you can all utilize those queries to make A0 go down and go down to 1. Sorry, go down to 0. This should make sense. All right. So I know some initial queries in the start are useful for me. They can make A0 go to 0 if A0 was not 0. This is again highly assumption that I'm taking over here. Try to visualize this part. But the main idea over here is why did we sort was to first of all get this that okay, when queries are sorted, then we have better else to take in the first location. But the other part over here is if I talk about so let's say there were 4 queries which had L values as 0. So basically 4 queries were helpful for you because they could have converted A0 to 0. Let's say A0 was 2. So to convert A0 to 0, you will only require 2 operations, right? You will only require 2 such operations to cover. But the number of queries you had were 4. So this makes us raise next question, that is, greedily, if I have 4 queries which covers, but I only want 2 queries to use, which query should I take? Should I take queries which have, since L are all same, so the only probable factor now to compare is R. So should I take queries which have a larger R or a smaller R? And this is where our whole greedy idea lies. Our greedy idea is we needed to track somehow where we can consume the queries to decrement our every ith number. But if we consume those queries, we have to make sure greedily that our consumption is dependent on larger R's, larger R values. This is the greedy idea. Why larger R values? This is something like, why larger R values? Because larger R values are bound to give me, this is larger. Yeah. So why larger R values? Because larger R values are bound to give me a better range, right? Assume this. Let's say you have R1 as 10 and R2 as 100. So would you prefer that you take L2, R2 or would you prefer to take L1, R1? Of course, you would prefer to take L2, R2 because it is giving you the power. It would always be better that you have the option to cover a larger range since L2, R2 covers numbers from 0 to 100. But in your first query only covers numbers from 0 to 10 index. So will I not prefer that I'm able to have a grip or power on numbers for a farther range so that later on if I try to use these queries next time, they would give me this power and numbers that extend even after the 10th index are in my grip, are in my power. This is why larger R works. This is why larger R makes sense greedily. This is a very visualized concept. Okay. Hence, taking L2, R2 is preferred over taking L1, R1 because of the larger R value. This is where this whole idea comes that if you have 4 queries, you're able to maintain 4 queries initially where you knew that, okay, this is the L's that were possible. But even in those 4 queries, which are the queries that would be firstly consumed by me. Those would be the queries which have a larger R value. Okay, and this is where it hints me that now the problem is all about implementation. How do I maintain this R values? What's the ideal way I use that? And since I'm always talking about prioritizing, consuming larger R values first, so on, this would hint me that I use a data structure, preferably a data structure which maintains priority, or to be very specific, should be a priority queue. Okay. So I'll give you a pseudo figure of what we would want to do. We would want to maintain an available priority queue, okay, and an active priority queue. Now, available priority queue is going to be a max heap, and an active priority queue is going to be the min heap. So this is again implementation difference. You can again do this wherever you want, however you want. Okay, if the rudimentary idea is same, your question should work. My idea is I'll take an available priority queue, I'll take an active priority queue. What would they dictate? Available priority queue would dictate the current queries which I think were available for me to consume, because those queries covered the AI number. But this available priority queue is a maxi, because in this available priority queue, I will shift the queries R values, and since this is max heap, it will always maintain at the top the largest R. So if I'm starting at an AI element and I'm trying to cover some queries, and I feel that, okay, the queries are being covered, they are going from left to right since they were sorted on L first. When I actually say that, okay, these are the queries useful for me, I will shift their R values to available priority queue. And since available priority queue is max heap, it will maintain larger R's first. Then once I have processed whatever queries I could have utilized from the from the query pointer running from left to right, I will stop and then I will ask myself, okay, can I have, do I have some active queries right now, as in queries that are currently into consumption? If yes, then okay, great, reduce my number by those active queries. Else, now I will try to say that I have some available queries with me. They are ready for consumption. Preferred they have the larger R values. Let's shift those queries to the active priority queue, which would mean they are currently active. They are currently being consumed. But to do that, why am I taking active priority queue be a min heap? So if you shift the R value at the top location, you have preferred the larger R consumption, but you shift that and you make it to be active min heap. Now in the active min heap, every time you have the top value, that would be the lowest R in consumption, right? Why is this coming into picture? Because remember this part, assuming you are standing at some ith index and you are taking a journey from left to right, after you have actually reduced the number from AI to 0, you would want to say or remove the queries which were currently under consumption, currently active, but are technically no longer used for you. And how do you make sure that happens? You can make sure that happens is by saying that whatever are the lowest R queries which are currently into consumption, but they are coming before I can pop them out. They are not longer useful for me. So let's say you were standing at this ith number, okay? Some I equals to, I'll just take an example. So let's say you're standing something like I equals to 3. So all the current active queries which fall before 3, which only would have covered the range before till 3, are no longer utilized, no longer useful for you. So let's not take that into picture. Let's remove them. That's why it would be very beneficial for us to maintain lowest R sort of a priority queue, so that I pop out the queries which have better R's considerably. So like if lowest R is there, so some query like this, lowest R, then you have some more larger R, some more larger R, then you stop. So you prefer that you remove this query first, then this query first, and then this query first before I equals to 3. So this is sort of a idea in this problem. Let's actually take a case that we have created on our own. I have drawn up a case on my own, and we'll try to simulate this whole idea, what we dictated on this case, and it will make much better picture. Okay, so I'll start off, I'll say, okay, the array is 1, 3, 0, 2, and the queries look like this: 0, 3, 1, 3, 2, 3, 0, 1. So first of all, I sort the queries, very highly preferred, because if I sort them, I have better else to take initially. So sorting them, 0, 1, then you have 0, 3, then you have 1, 3, and then you have 2, 3. Great. Now you have empty priority queues right now. This is available priority queue, and you have a active priority queue. Available dictates what queries can be consumed, and active queries are what queries are under consumption. Great. So now active queries active and available or are empty. You start off with a pointer, you go to the first number and you go to the first query. Is first query covering the first number? Yes, it is, because ideally it should, because we have sorted the queries. So that is why sorted made sense. Now you have the queries which cover the 0th index first place. So hence it will cover. In this case, is of course covering. So I'll say, okay, 0, 1 covers this first number. Great. Let's push its R value in available, because this is something that can be consumed later. It's available with me. So let's try to keep that into our light. Let's push the R value 1 in this available query, available priority queue. Great. Let's move on to the next query, 03. Does this query also cover this number 1? Yes, it does, because it's the range to 0 to 3. 03 of course covers the 0th index. So great, good to go. Let's push this R value. But now remember, available query is a max heap, so it will automatically make something like 3, 1. Which makes sense, because I am preferring the larger queries, larger R queries first, because they like 0, 3 is a query which is better preferred than 0, 1, since 0, 3 has the power to get a grip on larger set of numbers. All right. Now, once I go to the final next query 1, 3, I'll stop, because I know 1, 3 does not cover this number that is kept at the 0th index. So great, stop. Now let's start off with actually making this number go to 0. So I'll say, okay. Right now, do have some active queries. I don't have any active queries, so this number doesn't change. It still remains 1. Now I actually would need to consume some queries. So my available queries to consumption are the queries which were ending with R3 and R1. Which query will I prefer first? The query at the top, which is of this nature, that is 3, of ending with R equals to 3 value. So I'll shift this query from here to this, and I'll make it reach the active query, and this becomes the overall looking of how priority queues will look like. And once this is done, this number will of course reduce. This number will go to 0. And now I can stop, because this number has turned to 0. So I can move on and I can come to this next number 3. Now let's go on to the simulation. You are standing at the query 1, 3. Is this processable? Yes, this is processable, because this covers this particular value range. Great. Let's pop out this number. And let's say this number R, and now your available queries also looks like 3, 1 again, because 3 is preferred. Now after that, when you move on to this next query 2, 3, it doesn't cover this number kept at the first index. So you will now have to actually check for if this number right now can be actually converted to 0. So first from 3, we'll say, okay, what are the active queries? The active queries are queries that were like the overall active queries right now in picture or consumption are only 1. Remember, you had already processed this query and you have sort of activated it. You have activated it. It's active right now. So this query can be consumed. That's why overall the size of active priority queue can be taken out from this number, that is 1. So this becomes 3 minus size of active priority queue. This becomes 2. So this query is processed. Now, of course, this has not turned to 0. So I want more queries to process. So I'll say, okay, next available query with me has R equals to 3. Yes, process it for me. So 3 comes into picture over here. The next also 1. So 1 also comes into picture over here. So like basically you like empty out this available query. This basically becomes nothing. This is all left with nothing, empty. But your active priority queue has now, because of a min heap nature, converted to 1, 3, 3. And you have processed 2 queries basically. So that has converted to 2 to 1 to 0. So this number has turned to be 0. Now, can you see the idea over here that why active queries are now looking like 1, 3, 3, or why were they prefer to be min heap? Because now you will understand this. Let's move on to the next number. The next number is 0. So it doesn't require any change. It's not a worry for me. So it's fine. Let's go to the next number 2. Now, when we are actually at the next number, when we are we're at the next number 0, before actually moving on to 2, we understand that the query that is kept at this location has an R value of 1. But the index you're right now standing at is the index 2. So this is index 0, 1, 2, and 3. So you're standing at the index 2. So after you have crossed this query's largest R, this query's R, not largest R, this query's R, do you think this query now is useful to you? No, it's not, because it has the R at 1. So why will I use it? I don't need to use it. It's not going to give me any useful case, because this only covers till 1th index. It only goes till this limit. So let's remove this. And that is why active query had to be of the min heap, because it is maintaining lowest R's now, right? Lowest R's for me, as we discussed, lowest R's now. So I'll remove and pop out this top from here. And I'll say, okay, don't pop out 3 now because 3 of course still covers. So 3 is not something I don't pop out, but 1 is something I still pop out. And after this, I'll finally move on to my next number, that is 2. Okay, now same idea again over here. From 2, I'll say, okay, is there any query more to process? No queries more to process. So because this has already been processed, not an issue. Let's go to the active query size. It is 2. So this number changes to 0. Okay. And now all the queries after processing can be removed. So 3 and 3 queries are like till before equal to this indexes. So they can be removed also. Removed and removed. Basically your finally queries pop out. This also becomes empty. So this is the whole idea. You have actually utilized the whole queries very smartly, and you have actually made your whole 0 array go to zeros. Now, remember, when we did all this process, when we were doing all this process, we were maintaining a variable which told me how many number of times did you actually use some query to be shifted from available to active. Remember, we did it 3 times. Once it was like 3 there, then 3 shifted, then there was like 1, and then there was one more 3. So these 3 values is what shifted. Since these 3 values shifted, it meant that, okay, you ideally only consumed 3 queries to get your whole array to a 0 array structure. But active total queries that were given to you were 4, which means if you are able to maintain a variable over here which denotes the movement from available to active priority queue, it would mean that the answer can be written queue dot size minus whatever is the successful consumption, something like that, like successful consumption. So queue dot size minus successful consumption of queries is going to give you the redundant count of queries which you can remove. Even if you never utilize those number count of queries, you will be good to go and everything will work. Okay, so this is the whole problem. This is the whole idea. Let's look into the code part now. Okay, I'll expand this out. So just how we process the whole stuff in our mind is what we are going to do. So we have a priority queue, that is, if you create a simple priority queue, that is basically the available end indices, available priority queue. This is of the max heap nature, and then you have a min heap, that is the active end indices. So that's the active priority queue. And then you sort the queries first. Then you have a successful queries variable, that's the how many queries you were able to process finally, consume finally. Then you have a query pointer that runs in the queries parameter. Then you of course have an index that runs in num size. So you run through every number. Then first of all, what do you say? You say, okay, let me add to available indices the queries R values which I think are equal to, whose L values are equal to index. If L values are equal to index, that means they would cover the range. So their R values is what I would push. Since available end indices is a max heap, this would automatically make available indices, all available indices R values I push, to be sorted in a manner where I have a descending order, largest R comes first. I'll increment my query pointer till it's possible. Then I will decrement whatever is the active queries I'm right now using under consumption from my nums of index. Then till I feel nums of index is actually positive and I have still some available queries to process, I will do the shifting, because I know that if it's still positive, which means it has still something to go. So I need some shifts from available queries to active consumption queries, active consuming queries. So I'll say, okay, till my available end dot top is greater than equal to index, it still covers. Let's take this query into picture. So successful queries becomes +1. Push this available queries top, that is the R value, largest R value, to the active indices in the query, that is the min heap now. Active indices priority queue, sorry, and then pop it out. Then decrement your nums of index by 1. So this happens and happens till either you make nums of index turn to 0 or you have no more queries to process. And now where's the -1 case, right? We also had a -1 case. -1 case, of course, comes into picture is after everything has been done. You removed all the current active consumption queries from nums of index, and then you took some more queries into picture from available indices, and still you were not able to make your nums of indices go equal to 0. Then you know that you will never have enough queries to, like, the queries are not even enough to make that current index turn to 0. So you will have to return a -1. And if this doesn't run, then the final thing would be remove the expired queries or the queries which are no longer useful for you from the active indices. On what basis? If their top is equal to index, or it's like less than equal to index. Technically this would be equal to index because we are technically moving the indices possible which are equal to that current index only. So I'll pop them out from the active end indices. And then I come out of this whole loop, I know that queries.size minus successful queries is the answer, because this is the queries I was able to consume. So the redundant queries would be total minus the processed queries. Okay. So this is the final piece of code. I hope this is clear. Now the time complexity, if we discuss, is going to be a bit complex. I hope I am able to make sense. What will happen over here is, try to understand. Basically, you have a for loop over here that's running from 0 to n size. That's the num.size. So you can imagine that you have n slots. You have like n slots. You have like slot 1 plus slot 2 plus slot 3, like slots of time complexity. In every slot, in every iteration, or slot to be specific or iteration to be specific, you are doing something. So if I'm able to add up all the possible time complexities that are coming for every iteration, up to n iterations, that's my answer. That's the basic idea of time complexity. This is something everyone knows. So why am I doing this is because now from this picture, it's going to be very easy to get the hold on time complexity. If you now go inside this for loop, everything that you're doing right now is either push or pop, right? Either you push in the available end queries or you pop in the available active end queries. Now, since you're talking about every R value, it one time gets pushed, second time it gets popped. So every R value either is pushed or popped. Basically, it is always pushed and popped. So that means that I have 3 while loops. Every while loop will have a log based time complexity for pushing or popping. And since there are 3 while loops, I will have 3 into log, and how many push and pops can happen is dependent on the number of queries. So that would be total of m. That means I would have, like, whatever this sum turns out to be, this sum is actually going to be something like a 3 into m into log base 2 of m, or not m, actually I can take this as q, where q is the query size. Now 3 into q into log base 2 q can be simply written as q log base 2 q, because 3 is a constant factor. I don't need to take that in picture. 3q into log base 2q, or q log q, is basically the overall time complexity of this inside while loops. But here comes a very important point. In addition to q log base q, you will have to report an extra n factor over here, which is the number of elements, because you're taking up extra accessible time to actually get every element into picture. And like, you can understand this like this also, that if let's say no queries runs, then basically you would be running the for loop to be empty. And if you run a for loop to be empty, it basically means that you would be definitely doing some iterations, like some number of iterations that would be, again, can be reported in n order. So you can have this plus n factor to it. That's where the overall time complexity should technically be like q log q plus n. Now, of course, if we talk about q and n, both were in 10 power 5 order. This is all 10 power 5 order, this is all 10 power 5 order. So whichever supersedes the whole idea is going to be the better part. Larger chunk would be q log q only if q is more than n. So we know that time complexity is reported as O of q log base q plus n. This log q is again coming from this push and pop stuff. I don't need to write that part. And q into log q is because you want q queries to be processed. So every query is getting processed in log q terms, and then this extra n. Now, what about the space complexity? Space is only dependent on the number of queries, that is O of q, because you are only maintaining parity queues and they are only maintaining q queries at max. So that's the number, that's the extra space that you're using for queries. And then you will of course have some queries, the space from the nums array, so that can be q plus n over here reported, which gives you the total space. Okay, so this finally wraps our problem. I hope this is clear. Definitely a very implementative based problem. Idea was not very tough, but how do we get this whole thing running is what was making this problem to be a bit on the tougher end. Let's move on to our problem 4. Okay, so the final problem of this contest: find the maximum number of fruits collected. Okay, there is a dungeon, game dungeon comprised of n into n rooms arranged in a grid. You are given a 2D array fruits of the size n into n, where fruits of I of j represents the number of fruits in that room I of j. Great. 3 children are playing this game with initial positions at the corners 0, 0, 0 and minus 1, n minus 1 and 0. Now these children will make exactly n minus 1 moves according to the following rules to reach the room n minus 1, n minus 1. Great. The children 0, 0, if it is at I, j cell, then he can make these sorts of moves. Then if it is the children talking about 0, n minus 1, then if it is at current cell I, j, then it can have these sort of 3 moves. And same is for the last children. It also will have these sort of 3 moves. And then what is given? When a child enters a room, he will collect the fruit there. If 2 or more children enter the room, then one child will collect the fruit, and the room will be empty after that. They leave. What is the maximum number of fruits the children can collect from the dungeon? Okay, so what we have done is we'll take example 1 and fully understand it so we get a grasp of the problem. I have taken the same picture over here and let's try to discuss on that. So I'll take this pen, let's say some like a yellow pen. Yeah, that would be fine. So basically you have 3 children in this n cross n grid. Okay, so over here n of course is 4. You can understand that is why this is like a 4 cross 4 grid. You have the numbers, this is like 0, 1, 2, 3, and then this is also 0, 1, 2 and 3. Okay, so basically you have children. There is one child C1 kept over here. This is the other child C2. I'll take a different color, maybe should be visible. Yeah, this is the child C1, this is the child C2, this is the child C3. Okay, so now C1 of course is at 0,0 cell, C2 is at 0,3 cell, and C3 is at 3,0 cell. Great. Now there are some movement restrictions of how do they move. If you go back, basically this is the person that we start off with. We want to make ourselves go to the final location, that is n-1, that is basically 3,3 in this case, because n is 4, so n-1 is 3. So basically every child somehow wants to come to this room. C1, C2, C3 all want to land up in this bottom right final room. To do that, they require exactly n-1 moves. It's a condition that they have to make exactly n-1 moves. This is like applicable on all 3. Alright, but added to that, every child has individually there some conditions. What is that? Let's understand those conditions. Basically, C1 child, C2 child and C3 child can make specific sort of moves. If let's say I'm talking about the first child 0, 0, if he is at an I, j cell, I can move to I plus 1, j plus 1. So what is I plus 1, j plus 1? If let's say this is I, j, okay, then I plus 1, j plus 1 is basically this direction. I plus 1 that is come down, and also j plus 1 that is go right. So j plus 1. What is the next? I plus 1 j and I and j plus 1. So I plus 1 j would be same column but coming down, and I and j plus 1 would be going on the same row but next column. So this is the movement that can be done by this first child. So I actually draw this green so it's much more clearer. Like this, or like this. Similarly, if I quickly get for C2 and C3 child, it's going to be very, very clear. For C2, basically C2 moves I plus 1 j minus 1, I plus 1 j, or I plus 1 j plus 1. So basically I plus 1 is always there. That is, I always move in the bottom row. So I plus 1 j minus 1, I plus 1 j, and I plus 1 j plus 1. So now j plus 1 index is not there currently, but imagine it could have been there. So that is the movement I could have done. Okay, it's not necessary I do that. It could have been done. Great. This should be clear. Now I'll change pen to blue. We have child 3. Child 3 can move in the same manner. If you get this grasping quickly, j plus 1, j plus 1, j plus 1 is always there. So you always want to move the next column, but you have the previous row, current row, or the next row. So basically move like this, or like this. This is actually the movements that are allowed to C1, C2 and C3. So first of all, they want to make exactly n-1 moves. Okay, this is very important. So over here, if n is 4, they actually want to make exactly 3 moves. Okay, 3 moves. Okay. Now, what are they doing when they make some moves? They're of course collecting some fruits. These numbers that are given, they represent something. They represent the fruits. So over here in this cell, it's basically 10 fruits. This says 15 fruits, 12 fruits, so on, so on, so on. And what's the target? The target is I want to collect maximum number of fruits. So basically, if you make some child go from its current location, move it, use 3 moves and make it come to the last cell, on the way of doing that, on the path of that child, he will collect the fruits he can from the cell he enters. Done this for all the 3 children, get me the total fruits collected and make that largest possible value. Okay, so they have actually given you a very good GIF over here. That's an animation that's running, and that will help you get the whole answer of why answer is 100. So if you realize that the first child starts over here, that is this first location green, you can see that child moving to 6, then 11, then 1. So basically he is using 3 moves. 1 to 6 is 1, 6 to 11, 1, 11 to 1 is 1. So 3 moves, that is clear. Okay. And the movement in the direction which he has done is also allowed, because he was allowed to move diagonally like this from top left to bottom right. So he collected 1, 6, 11 and this 1 fruit. Basically that gave you this much answer of the fruits that he collected. Then if you talk about the red child, red could have moved bottom left to the 8th position, then bottom right again to 12, and then just a bottom position, that is 1. So he collected fruits 4, 8 and 12. Now he cannot collect fruit 1 again because of a very simple sentence. Of course, you don't want to collect fruits once more if it has already been collected. So one fruit was already collected in the cell by child 1. So this red child won't collect that part. So you only get the answer 4 plus 8 plus 12. And then the blue child follows the path from 13 to 14 to 15 to 1. 3 moves again, collects 13 plus 14 plus 15 fruits. Effectively lands up with you 100 fruits, and this is arguably the largest. Okay, so I think we get the whole problem. We have understood the example. You can pause the video and even get a grasp of the second example, and you will realize that, okay, what's the problem totally asking you about. Now, this problem is a very clever and an observational based problem. Okay, first of all, we can ask ourselves that, okay, there is a child 1, there's a child 2, there's a child 3. Let's focus our energy on child 1 for now and imagine what sort of a movement is he doing. So let's go back to our diagram. We can see over here a very important point that C1 as a child moves like this, or like this. Okay, that's great. Now the question is, right now in the problem also you saw he moved from 1 to 6 to 11 to 1. Very clever indication of how example cases help us is over here. When I saw that C1 would have moved from 1 to this location 1, he took the path that was this diagonal path from top left to bottom right. Now I asked myself, okay, great. He does this thing, that's fine. But if I talked about C2, C2 could have taken a path like this also, from 7 to 12 to 1. But he took this path. So basically, for C1 also, maybe there were some different paths possible, right? Over here he took this path, so he took 3 moves. Fine, maybe there was some other path which also gave 3 moves. That got me thinking. But the argument that rises over here is, for C2, it was possible to take like multiple paths. Some path like this, maybe some path like this. Those were within his constraints of movement and also give you 3 moves, or exactly 3 moves. But for C1, that's not possible. Why? Mathematically understand this. We are currently at 0, 0 location, and you want to go to n-1, n-1 location. The minimum number of moves you would require to do that is actually n-1. And that is only possible if you move diagonally. Because if you take any other path, let's say you went like this, then like this, then like this, and then like this. Although you will reach the last 3, 3 cell, but you will take more than n-1 moves. So if you don't take the direction of this diagonality from top left to bottom right, you will gather more than 3 moves, and that is not allowed in the first place. We have 2 constraints on C1. He takes 3 moves and he does that in his direction that he can only do. So although directions will be good to go, you can of course move like this, then like this, then like this, and then like this. So directions are good to go, but the count of moves will increase because the lowest moves you had to do from 0, 0 to n-1, n-1 were actually n-1 moves or 3 moves. So anything beside that is not possible. This actually made me realize that, okay, C1, although looks like has more paths to follow, it is not the case. C1 basically have only one direction possible for him, that is only move like this. So this restricts me and puts me in a case where I can say C1 will collect all the fruits that are there from the diagonal of top left to bottom right. And this is sort of, you can say it's sort of the space where C1 is going to revolve. This is the only path, actually not space. This is the only path which C1 can follow because this is the only path that satisfies the condition of 3 moves. Okay. So I hope this observation should be clear. Now, building on this observation, when I realized this observation, I asked myself next time, okay, great. C1, now I saw, had this idea initially that it could have taken some many paths, but I realized it only had some restriction, and some restriction I created myself, which made me realize it only moves in this diagonal sort of a manner. So I said, okay, maybe I can try to focus my power on C2 and C3 also. Maybe right now C2 looks that it can move anywhere, but is that actually true or fundamentally true? The argument is no, it is not fundamentally true. Why? If you carefully observe, same idea is on C2. C2 also requires to take up exactly 3 moves. So let's say that you took a path like this. You went like this, like this, like this. Okay, great. You landed at the last location. All right. You took a path like this to, like this to this to this. Okay. Landed up with 3 moves again. But if you took a path like this, then also to 10, now at this cell, you would of course want to come back to 3 comma 3, but from 10 you can only come down, and the best you can go is down to the right cell, that is at 15. And after 15 there is no move that helps you go to 1, because there is no move that only makes you go in the right direction. This is actually the speciality about C2. If you observe, C2 is always coming down. Out of the 3 options that it has, it can move either to left, stay there, or right in terms of columns. But in terms of rows, if it is at the ith row, it will always move to I plus 1th row. Which means by visualization, C2 after 3 moves has to land in the last row. Currently it's at the 0th row. It will take one move, one move, one move. So basically 3 moves or n minus 1 moves, and it is bound to land at the last row. So if it has bound to land in the last row, I have to somehow make sure it doesn't land on the last row. Also, it lands on the last column. That is why it would make sense it lands at n comma 1, n comma 1. So to do that, I should understand that I cannot cross this boundary of green. Basically, this C2 child cannot cross this green boundary, this green diagonal, because if it does, then there is no possibility of coming back to 3 comma 3. Only if it sticks to the boundary above, or in this is the segment of space where C2 sticks, is when C2 can actually take some possibilities of paths and actually come to this last 3 comma 3 location. This is our next observation, which came stemming from the initial case of green or this child C1. Okay, and this is what made me realize that okay, C2 overall as a child has a restricted sort of a right angled triangle on top, or on the top segment of that green diagonal that we drew. Only these locations are where C2 can explore. The possibilities which I was talking about for C2 only happen in this segment. They don't cross the green border. Now, when I was able to hit this idea, it made sense that this is also going to be applicable on C3. Because basically, if you observe very carefully over here, if you take these moves and if you just rotate them like 90 degree over here, this basically it gives you these moves, right? Just make this shift over here, take your hand, take your fingers and rotate it like this in 90 degree, like this in 90 degree, you get this part, right? So somewhere or the other, C2 and C3 are making same sorts of moves. So my idea that C2 had a restriction on this upper right angle triangle in terms of movement is kind of the same on C3. It has the restriction only on the bottom right angle triangle. If C3 crosses this whole green border and like green diagonal and comes to this location, then it will never be able to come to 3 comma 3, because same idea, C3 is always making a move in the direction of j plus 1, that is next column. So after 3 moves, it has to land in the last column. To make sure it lands in the last row also, it's not feasible to cross this green diagonal. This is actually the main ideas behind the problem. Okay, so observation 1, C1 only moves in the diagonal. Observation 2, C2 moves in a restricted space that is above the diagonal, and C3 moves in a restricted space that is below the diagonal. Which means now this problem is independent in nature. That is, C1's answer is independent. Maybe I can name this. I can say that, okay, C1 had an answer called fruit C1. That is the fruits calculated by C1. This was the answer that is fruit C2. And this was the answer that was fruit C3. Since the search spaces are independent, which means that I can get a accumulation on the answers, best possible answers that come out of all their movements, and add it up. That will definitely give me the overall fruits collected in the whole problem. Hence, this makes this problem very, very unique and very clever. Okay, so when it comes to C1, answer is going to be direct. You can say, okay, great, just move and take a sum from this diagonal and you will get the answer of fruit C1, that is the number of fruits collected by C1. For fruit C2, basically it's a sub problem where I'm saying that you started off with a cell of 0 and minus 1, or basically 0, 3, and you wanted to move to 3, 3. You wanted to make exactly n minus 1 moves, and your search space was only limited in this order. So we can actually take some extra checks, but if you realize this is a very clever condition we are trying to use, we know that C2 if reaches 3, 3 will only move 3 times. That's very clear. So we don't need to keep any extra checks. What we can simply do is we can make sure that our base case can be If it finally lands at 3,3 is when we want an answer to be gathered. If it lands at any other locations and it's not 3,3, or if it jumps the boundary or something like that, then I can just return a very low answer because I want to maximize my total fruits. So I can return a very, very low answer so that it helps me take that base case into consideration. So basically, this becomes a sub problem where I'm starting off with an I, j cell. I have 3 states to go. So this creates some sort of a recursive solution in my head. I have 3 possible ways to explore, and every I, j cell has that possibility to finally, this whole recursive sort of a solution is going to end when we land at n,1, n,1. And since the independent search space is maintained for C2, whatever answer comes from calculating the recursive states on C2, that answer, that number of fruits is only possible to be collected by C2. C3 will not interfere there, neither will C1. So this creates a recursive solution, and because we don't want recursive solution to give us a TLE, we would of course want to memonize that. So this basically finally gives us an DP problem. This lands up being the whole problem in a DP based solution where you would maintain state, preferably the cell values I and j, and you have 3 options to explore, and you maximize out of all those 3 particular options. You can make this DP work for case child 2, and you can make a same sort of a structure DP memoized for child 3. Why are different DPs or like different sorts of recursive functions? Because C2 moves in a different manner how C3 moves, so you would require different explorations, hence different recursive functions make sense, right? Maybe you can be very smart and create a single function, somehow manage that state, but that's also fine. To make a code look much more cleaner, we can take 2 different states. That would also be fine. Okay, 2 different recursive functions, sorry, that would be fine. But the rudimentary idea of how do we get the answer is going to be the same, because this is sort of a sub problem, right? If I would have given you the problem separately, then you would have solved it. But this problem is kind of tough because it clubs all sorts of like 3 ideas together. Get this, and get this. Okay. Great. So now I'll just we can discuss a small pseudo code of how the DP should look like. It would be some sort of a recursive function, right? So something like a helper function. We would of course want to maintain I, j states, right? And now what would we want as base cases? Of course, one base case should be that are we in the boundaries or not, right? If you're not in the boundaries, like if you cross the if you cross the grid boundaries, go before 0, after n, something like that. So you would want to return a very negative case because you want to maximize. So if we are out of boundaries, we would want to return something very, very negative. Ideally, it can be like something like 1e9. So this is like a very good base case, right? Other base case can be, of course, that if you're standing at I equals to n-1 and j is also equal to n-1, that means you have basically reached where you wanted to reach in that child case. So this is where you can return 0 because we are already taking fruits into consideration. So this is a good case. You want to take this, hence you can return 0. It doesn't hamper our answer. 0 will make sure that I still take the max. So this kind of becomes our base cases, right? Base cases. Then of course, because this is a DP question, you would have one line for whether DP of I of j was already there. If it was already there, great, just return it directly. So return DP of I of j. This is like the memoization sort of a solution. And then you have 3 options to explore. So you will have option 1, option 2, option 3. You will get those options individually for all, like if you're talking about the C2 child case, you will get those options. And out of these options, the max option plus the current fruits value, that's fruits of I of j. So if you're at I of j cell, then you will collect those fruits and then you will recur for the next 3 best options. And out of that, get the max and add that to your answer. This would be the location stored at number stored at DP of I of j. And when you finally complete this helper function, you will get the best possible answer for C2, considering you have taken the moves or options for C2's case. Next, you would maybe call some other recursive function. Looks like the same order, but now the option 1 to 3 would be bothering about the cases of C3. And C1 case is direct. We don't need a DP for that because we only wanted to explore this diagonal. Okay, so this is the problem. Very, very fun problem. Let us now look at the code part. Okay, so I'll actually expand this out. You have the maximum collected fruits answer, the function. You have n as the fruit size. Then you have an answer variable. Then what I'm doing is I'm basically getting first the answer coming from child 1. So every fruits of I is getting added to answer. Why I of I? Because I'm talking about the cells on this diagonal. So this is like 0, 0 cell. This is like 1, 1 cell. It's like 2, 2 cells, so on, so on, so on. So basically cells which have I and j same are the cells on this diagonal. That's why I would want to add fruits of I, and then I will make that value as 0. Why? Because it's collected. So I don't want that to be collected again. So it would make sense that I reset it to 0. So whenever if C2 somehow collects it in its recursive function or C3 collects it in the recursive function, we basically collect nothing. We basically collect 0. Okay. Now we have a DP at the very top. I have a global DP of 1000 cross 1000 size. So I want 1 base indexing. That's why I've taken 1001, 1001, that extra 1 index. Then I have mem set it out to be -1 initially, everything. Then I call for the recursive function. So I have first called the recursive function BL. BL is basically bottom left. So basically I have calculated child 3 first. Child 3 starts with n-1 and 0 at its initial location. And you have fruits and n to be passed. So if you go to recur of BL, if you are in the boundaries, like if you're not in the boundaries, that is I or j becomes less than 0 or they cross n boundaries, return -199. If you actually land up at the correct cell which you wanted to do, return 0. If it is already pre-calculated, return dp of I of j. Else, 3 options. Fruits of I of j plus, this is the recursion here. So if you are at I comma j cell, you go to I-1 j plus 1, I j plus 1, I plus 1 j. J plus 1. Get these 3 options. Max of that is stored in dp of I of j. And then you can reset the back dp to -1, all cases. And then I will recur for tr. Tr is top right, so that's basically child 2. Same idea, like if you can see, it's basically the same code. Only these options will change. Now I will recur for I plus 1 j minus 1, I plus 1 j, and I plus 1 and j plus 1. Get the maximum again. So 2 separate recur functions helps me handle C2 and C3 childs. Get that total answer. I'm of course adding that to answer every time and return it. This gives you the net number of fruits. So a very, very clever problem. Now, what is the time complexity? We have basically calculated that we are maintaining states of I and j both are like, basically they are indexes. They can run maximum in 1000 order. Since you have 2 states maintaining, basically this recur functions after memorization is running in n square time complexity. This runs in n square. This also like runs in n square. Okay, this is very important. So overall, like this function is running in n order, and then you have this functions running in n square order. This is n square. This last thing is also like n square. So which means that overall our superseding term is definitely n square. So I can write my time complexity to be O of n square. Now n is in 1000 order, which means this is like O of 10 power 6. 10 power 6 definitely works whether within my boundaries. What about space? I'm using space for the dp. So that space is basically n square order again. And like I have some space from the fruits vector also, but then it's only in 1000 size, so that doesn't matter a lot. So I can take that n square is the better term to report, which is again space in 10 power 6 order for the dp. Space and time all are within my boundaries. Okay, so definitely a very fun and very observative based problem. Definitely that is why it makes it very hard. It was basically a accumulation of sub problems. You have to identify that dp was getting applied, and this finally ends our post contest discussion. So I hope you like the video. Thank you for watching.